Modern AI infrastructure processes data at high densities, while 5G networks operate at frequencies measured in the tens of gigahertz. At these extremes, hardware operates in an entirely different physical regime. Standard circuit theory assumes electrical pathways are isolated. In this model, you send a signal down a copper trace, and it arrives exactly as transmitted, unaffected by its surroundings. When extruded into 3 dimensions, a modern server board is a dense block of multi-layered printed circuits, packed to minimize latency. At high frequencies, these tight geometries act like broadcast antennas. Invisible electromagnetic fields emerge, and concentrated thermal hotspots bleed across the board layers. These physical forces, rather than logical code errors, are the primary cause of signal degradation and hardware failure in high-speed systems. This presents engineers with a specific problem: mapping and mitigating forces they cannot see, long before a physical system is actually built. In the context of AI hardware and 5G connectivity, unmanaged electromagnetic physics leads directly to catastrophic system failure. The traditional hardware development lifecycle is linear. Engineers design a circuit, manufacture a physical prototype, test it in a lab, record the failures, and repeat. This flowchart compares that traditional build and test cycle against a digital timeline. When dealing with complex architectures, manufacturing physical iterations is slow and consumes significant budgets. Simulation is vastly faster. Furthermore, physical measurement at 5G and 6G frequencies introduces technical errors. The mere presence of a testing probe adds new conductive material, which changes the exact electromagnetic environment it is trying to measure. Hardware engineering now requires a transition to digital prototyping, where physical validation is the final step rather than the first. CST Studio Suite is the specialized computational engine built to facilitate this transition. It operates on a foundation of advanced mathematical solvers designed to process high-frequency, low-frequency, and static electromagnetic fields. These solvers process the Maxwell equations across millions of spatial data points, allowing engineers to predict the exact physical behavior of a device before manufacturing a single component. Computing failure through digital simulation is the only viable method for scaling the next generation of electronic infrastructure. The primary threat to signal integrity in high-speed hardware is electromagnetic interference, or EMI. This 3D model isolates parallel signal traces. In tightly packed environments, any trace carrying a high-frequency signal acts as a transmitting antenna. As current pulses through the first trace, magnetic fields expand and couple across the gap, intersecting the adjacent trace. This is crosstalk. Crosstalk degrades both signal and power integrity. The induced current distorts the intended waveform, lowering the voltage margins required for the system to register digital data. In practical terms, this translates to data loss, high error rates, and increased latency across AI server farms. To contain these stray fields, hardware must meet rigorous regulatory standards for electromagnetic compatibility, or EMC. CST Studio Suite's analysis tools allow engineers to map these exact interference patterns. By analyzing the data, designers can adjust trace geometries to achieve EMC compliance digitally. Controlling electromagnetic interference is now a matter of optimizing spatial geometry through simulation, rather than simply relying on different manufacturing materials. Analyzing electromagnetic problems in isolation yields incomplete results. Circuit boards do not exist in a vacuum. Modern compute environments, particularly AI hardware, generate immense levels of thermal energy that change the behavior of the electronics. During peak processing loads, clusters of AI accelerator chips output intense, distorting heat that saturates the surrounding hardware. This heat alters the physical properties of the materials. As temperature rises, a material's dielectric constant and electrical conductivity shift. This top-down view shows a circuit trace beneath a thermal gradient. As the signal encounters hot zones, it warps the electromagnetic behavior, scattering the signal flow. CST Studio Suite solves this by using tightly coupled multi-physics simulations, analyzing both thermal and electromagnetic effects simultaneously. Engineers must solve a continuous feedback loop. Electromagnetic activity generates heat, and that heat subsequently alters the hardware's electromagnetic activity. Total system reliability is impossible to guarantee without computing thermal and electromagnetic forces as a single, unified physical system.
High-frequency engineering requires navigating a massive parameter space. Designers must balance variations in component length, width, and spacing. Manually testing these variations, even in a digital environment, creates a bottleneck that halts development. A wireframe model of an antenna array linked to an automated script. CST Studio Suite integrates with Python to drive rapid design evolution. The script autonomously forces the antenna structure to adjust its geometric parameters, analyzing output and self-correcting to reach target performance. Running thousands of these multi-physics permutations simultaneously requires immense computational horsepower. High-performance computing and cloud-enabled simulations provide the engines required to process these massive datasets. In telecommunications, this automated workflow is necessary to finalize the complex, densely packed antenna arrays required for 5G. The same framework applies to the automotive sector, ensuring the precision and reliability of modern vehicle radar systems. Pairing automation with cloud computing transforms simulation software into an active, intelligent design generator. A digital twin is a virtual replica that accurately reflects every physical parameter of a device. A side-by-side comparison of a simulated 3D radiation pattern and real-world data captured in a physical testing chamber reveals the measurements are nearly identical. This level of accuracy compresses development cycles, minimizing the need for physical prototypes and reducing costs. By achieving compliance and reliability in the cloud, businesses prevent late-stage physical failures. This simulation framework supports the foundational research required for 6G networks and expanding IoT devices. In smart cities, millions of edge devices and automated systems continuously transmit wireless data across dense urban environments. As connected electronics become ubiquitous, the requirement for preemptive electromagnetic simulation becomes absolute. CST Studio Suite provides the essential computational bedrock required by engineers to build the physical reality of our connected future.